Hi, this video is for Environmental Engineering 670, Hydrology and Drainage Control on the 27th of February 2019. This is class number 7 of the semester, and before we get into the lecture, a couple of announcements. First of all, homework number 6, which is related to evaporation, the topic of last week's lecture, that assignment is due today, so please upload it to MU Online or send me an email if you're having any questions on that. Our first midterm exam of the semester is going to be held on Wednesday, March 6th, and so that's a week from today's class. That's going to be live in person in the engineering building, so we won't have a recorded meeting that week. We'll actually have a live meeting. The exam is going to include concept questions where you're going to just be working from your memory, and then the problem-solving questions where you'll be allowed to use outside resources. So that exam is on Wednesday, March 6th. And then the next homework assignment will be due on the 13th of March, and that's going to include some questions related to both infiltration and also hydrographs. So that's a bit of a schedule recap. If you have any questions about that, please stop by or send me an email. So today's lecture is a combination of a couple of different topics. First of all, we're going to continue the topic of infiltration, which was started in class last time. We're also going to get into chapter 8 in the book, which kind of now starts bringing it together now that we've addressed rainfall, we've addressed evaporation and infiltration. We'll begin to look at some of the broader concepts that discuss how runoff occurs and how we quantify and express and visualize amounts of runoff. So that's the topic in Chapter 8 that we're going to be discussing today. As a reminder, these recorded lectures are taken from past semesters where I was live in the classroom with other students, and so there may be occasionally a question from one of them that you're not able to hear. I apologize for that, or there might be some incidental reference to a time or date that doesn't quite match up with this semester. But the underlying fundamentals, the concepts, they're all the same. And of course, the announcements that you have here on this slide and that I've shared with you via email, those are the ones that govern. So please let me know if you have any questions.
All right, so a couple of important terms, and I think that these show up in the list of vocabulary that you're going to have to be ready to define each of those terms for each chapter before the exam. And most of them are things that we've talked about in class, but there may be a handful of terms there that you'll need to just review the text to understand completely. The zone of saturation is where all of the void spaces are full of water. The zone of aeration can be broken up into a couple of subzones, but essentially that just means that some of the zone of aeration, the voids have air as well as water. The capillary zone is the closest to the water table. The soil water zone is closest to the surface, and the intermediate zone is just in between those two. So this is showing the capillary zone, which is where the surface tension and capillary effects has a higher water content than in most of the rest of the zone of aeration. This is showing the capillary zone. And below the water table, all of the voids are full. And so we could say if we're going to be measuring moisture content with this variable theta, so theta sub s means fully saturated. So at the water table, the voids are fully saturated. What this figure shows is that even above the water table, there's an elevated amount of moisture because of the capillary effect until we get to the typical water table content, the water content for the rest of the zone of aeration. So there's this gradual decrease in the water content, and there's a whole variety of void spaces in the subsurface. Like, remember that if you've got a mixture of sand and gravel and clay, there's going to be some paths from the surface down to the water table that have a relatively large diameter for the interconnected route to get there. There are going to be some places where there's just a series of tubes that by coincidence or by statistical anomaly have just really small diameter voids. And a series of small diameter interconnected voids is going to have a much higher raise in the moisture content above the water table. So the question is how can we describe the curvature of this and what happens to it during a storm? That surface tension effect is drawing the water up, but it'll also be drawing the water downward when water accumulates at the surface. And the way that we measure that tendency for water to penetrate quickly, remember, is the suction head psi. And that can be measured in terms of centimeters of water of suction. And one of the ways to measure that is with an infiltrometer. An infiltrometer can be as simple as just a ring of metal that you fill water into, and then you measure, like with a stopwatch and a ruler, how quickly the water decreases in height as it penetrates down into the soil. So this cross-sectional view kind of gives you an idea that when the water leaves the infiltrometer ring, it's penetrating downward, but it's also kind of going out sideways a little bit. And so that doesn't give us the best idea of what would happen during a rainfall event, because in a rainfall event, water would be spread evenly over the entire surface. So water wouldn't be going out sideways when it's raining. Water would only be going downward as it rains. So this single ring infiltrometer is not the best for estimating how the soil would actually absorb water. And so to kind of account for that, the double ring infiltrometer says if we have this outer ring of water that's being used to satisfy the sideward movement of water, then the stuff that's in the inner ring is just going to be satisfying the downward movement. So you can measure how quickly the inner ring drops, and from that determine, in the soil, how deeply it penetrated. And this outer ring is just kind of like causing the sideways movement. And so it's a way of isolating the downward effects from the sideways effects, and kind of like a field method for estimating infiltration rate. Of course, you have to be careful when using this not to scuff up the soil surface. You'd want to, when you're preparing the surface, have it be representative of the conditions everywhere else in the watershed as they actually are. So you'd try and put this into place maybe in several different spots and come up with a weighted average of the infiltration rate to get an idea of really what's going on everywhere in the watershed. If we take a unit volume in the subsurface, then the porosity is the ratio of voids within that total volume. And one of the earlier figures we looked at said that depending on the soil type, porosity kind of varies from about 25% to around 40%. Maybe in clay soils even higher than that, potentially. Soil moisture content is the ratio of water volume to total volume. Now, soil moisture can never go higher than porosity because, if all of the voids are full, then the water can't soak into the soil grains themselves. And so the maximum soil moisture content will be porosity. So the soil moisture varies from 0 up to the porosity. And when you have saturation, then soil moisture content equals porosity. What we'll be quantifying in a couple of the equations we look at is the change in water content during an event. So during a storm, when the water is penetrating down into the soil, it'll go from the initial water content to fully saturated. And so that change from the initial to the saturated moisture content will be delta theta. And then after the soil drains, then it has a residual moisture content of theta sub r. I think that probably effective saturation is something that you have seen before in soil mechanics class, and that is at a certain given point, like with the conditions as they are now, so this water content theta minus the residual water content, so that's in the numerator, and that equates to how much available moisture there is at a given time. So the difference between how much moisture there is now and how much there will be after it drains. So that That theta sub r is the residual moisture that really can't be used by plants, can't be extracted by draining. So the available moisture content divided by the effective porosity. So the effective porosity is saying, you know, the voids minus the residual content, it's the amount of water that could be there if it was fully saturated, minusing out the water that has nowhere to go because it's so tightly bound to the water. Of course, Darcy's law is one way of measuring soil characteristics and how easily water moves through a column of soil. And this is the figure that's in your book related to Darcy's law. Figures like this, I mean, because I've seen it so many times, it makes sense to me, but for whatever reason, having the column of water sideways makes it a lot easier for me to understand, at least. If we have a reservoir of water and the water is flowing from an upper reservoir to a lower reservoir, then we have some surface area. We'd call that A. And of course, the water is flowing at a certain flow rate Q. And the difference in elevations, so here's the delta H between the two water surfaces. Now, of course, it's the same thing here. It's just the column is vertical instead of horizontally oriented like I've drawn on the board. But then they're also showing that this needs to be a constant head. So on the right side, this little reservoir of water that's connected, they have an overflow and an inflow so that the water level never changes as the water's flowing through the sand. You have a constant head at the inlet and a constant head of water at the outlet, so that you always have the same H values, so it can come into equilibrium, and then you're measuring the flow rate through the soil as it does that. And Darcy's law says that there's some proportionality constant that describes the ratio of the area, the slope of the energy grade line through the soil. So that is the difference in heights over the length of the soil column that it's passing through. And that this proportionality factor K will tell you what the flow rate through that soil is going to be. And so if K is bigger, that means that you'll have a higher flow rate for a certain driving force. And it's this delta H divided by the length of the soil column that it's flowing through, that's the driving force. It's kind of what's pushing the water through the soil is the difference in elevations. And so here, where we have the higher elevation on the left, the lower elevation on the right, if you have a bigger deflection in H, that'll be a larger driving force and the flow rate will increase. So that's one way to have a big Q, is by having a big delta H. Another way to increase the flow rate would be to have a larger cross-sectional area. But really what speaks to what's going on in the soil is captured by K. And that's going to reflect like the size of the voids. It's going to reflect the charge of the particles. It's going to reflect those properties that are kind of inherent to the type of soil that it is. So hydraulic conductivity has units of length per time, and it's a really important parameter for predicting flow rate. Now, sometimes Darcy's law is expressed differently, like they'll call J the driving force. J would be the difference in elevations divided by the length. And sometimes Darcy's law is expressed in flow per unit area. So lowercase q would turn that into a flux if you are finding out how much flow there is for every unit of cross-sectional area that the water can pass through. So Darcy's flux has this formula. But I usually use the full hydraulic conductivity equation there. Just to refresh our familiarity with Darcy's law, let's finish by doing this example problem. If we have a fine sand, if you look that up in a table of typical hydraulic conductivities, it might tell you have hydraulic conductivity of 3 meters per day. So let's find out what's the flow rate in terms of liters per day. What's the flow rate through a column of soil that's 1 meter long, 25 centimeter diameter, and then where the head differential, delta H, is 35 millimeters. Well, eventually, let's get liters per day. It's going to give us, when you plug in the given values in terms of cubic meters per day, but it's pretty small. So if we multiply that by 1,000, we'll go from cubic meters per day into liters per day. I think we should see it's about 5.15 liters per day. The other time this semester that Darcy's law and K values is going to be really important is when we start talking about well performance. At the end of the semester, we'll spend almost our entire semester dealing with surface hydrology. But towards the end, we'll look at laws that describe when you're trying to pump water out of an aquifer, how much the drawdown in the water table affects the rate of movement towards the aquifer. And so those equations are pretty interesting, and we'll see K values again. So here's where we're heading next time. When we get together on Tuesday next week, we're going to look at methods for predicting how quickly water penetrates down through the soil. So experimentally, you can measure it directly, but you don't always have access to a site. You may have some basic information about the types of soil in a watershed, but maybe you can't actually go out and measure the infiltration. So there's a variety of different methods that empirically try and answer the question, how quickly is water infiltrating, and over time, how does that infiltration rate decrease as the soil voids become progressively more saturated with water. And we're going to begin with a video that illustrates water movement in soil. And it's kind of interesting, but it also makes a lot of the abstract theory stuff that we've been looking at in terms of diagrams and equations. It kind of brings it all to life. So I feel actually pretty fortunate that we've got this video. It's just one that I stumbled on last year on YouTube from university in the Netherlands. So let's see if we can get that going. All right, so what we're seeing is as there's ponding at the water surface, there's an increase in the water content, but it's not saturated until you go closer to the surface at a certain time. And so the way we're going to represent that in a diagram, there's a figure that shows here a wetting front moving down through the soil. So at a given time, it's fully saturated at the surface, but if you go deeper down, there's just a small increase in water content. And so consider this curve. What it's saying is, as you go closer to the surface, as you go up towards the ground surface, the moisture content is increasing until it gets to saturated. So this curvature is showing an increase in the wetting front. Now here's the water table. So of course, below the water table, it's fully saturated. So the moisture content is equal to the porosity at that point. But as you get away from that, the capillary effect means the moisture content decreases a bit. But then during a rainfall event, when there's ponding at the surface, the water penetrates not all at once. It doesn't go from like normal water content to fully saturated. There's this curvature here, like a gradual increase. And that's what we're seeing in this video, is we're saying that it may be saturated at this point, but this isn't fully saturated. If it was, it would be penetrating through the sand, because we see what happens when the voids are fully saturated. The sand immediately becomes like a highway for that water to pass through, because it has such a high hydraulic conductivity. So that hydraulic conductivity effect doesn't kick in until saturated conditions. So I just wanted to pause. We'll continue finishing the video there. But that's an important point, and I also wanted to tie it together with these figures that we're going to look at. And these figures seem abstract when you just see them for the first time and you're not able to kind of relate it to this visual representation of the water penetrating down through the soil. So what we're seeing is the wetting front go downward and outward because of gravity and because of the suction/tension within the soil. So those are the two things that are bringing the water down. But then the difference between full saturation and just an increase in moisture. All right, so in the video she talked about the movement of water when it's under pressure, and the movement of water when it's under tension. And water is under pressure when it's fully saturated. So consider the water table. I think we had a figure on a previous lecture. Let's see if I can find that one. Yeah, here. All right, so here's the pressure profile where we're down below the surface, and then here's the water table. So if you go below the water table, then the water exists under pressure, and it'll move one way. But when you're above the water table, in the capillary fringe, there's water that exists under conditions of tension, meaning that the attraction for the soil is sucking the water grains away from one another, and so that it's making space between the soil grains for those voids to have air in it in addition to water. And so the movement of water is different if you're below the water table, meaning saturated, or above the water table, meaning unsaturated. But we don't only have unsaturated flow in that capillary fringe. The unsaturated flow also occurs during a wet weather event as the water penetrates downward through the soil. So just as a refresher, remember that we have under the soil voids that are containing some water and some air. And this illustration is showing that we have solid particles that are covered by a thin layer of water, and then in the space between those thin layers of water, the air exists. And the smaller the grain, the more tightly bound the water will be to the solid particle, and the higher the suction or the tension will be when we have unsaturated conditions. Okay, so here's this figure that I already kind of showed you, that under ordinary conditions, the moisture content decreases as you move upward from the water table until you come to some like initial moisture content prior to a storm event. But then as water ponds at the ground surface, then the wetting front moves downward through the soil. And the speed of its movement depends on the gradient between the initial moisture condition and what it will be at saturation. It depends on the hydraulic conductivity of the soil, and it depends on how deeply ponded the water is at the surface. So there are a lot of things that affect how quickly the water is going to penetrate down. And so what we need is some sort of an equation that accounts for those factors, like an empirical equation that allows us to predict how quickly the water goes down. And why? Why do we care about all this? Remember, the rainfall that hits the soil has two places to go, broadly speaking. It can either go into the soil or it can go over the surface towards some point of concentration, towards a watershed outlet. So runoff equals rainfall minus infiltration is the broad way of looking at it. So during a rainfall event, as there's ponding at the surface, then the soil capacity to absorb water decreases. The rate of infiltration declines over time because there's going to be a smaller driving force. The initial driving force, what we saw is that at first in those videos, the water penetrated downward and sideways very quickly because there was a lot of suction. But then as more of the grains become filled, there's a smaller driving force that that suction or tension head decreases. Okay, so this is what happens during infiltration. At the surface, the voids are completely saturated because we assume that there's a little bit of ponding at the surface. The water is distributed into the soil grains completely, and so this curve of moisture content goes from fully saturated, and then there's this transition zone that's a lot like the capillary fringe. In the same way that there was kind of like the standard water concentration and then some connecting the curve between fully saturated and the middle ground where partially saturated. So this curved zone here, it's kind of like we've reversed that, and now this transition zone is the equivalent of the capillary fringe. And so some of the voids have small diameter, some of the voids have big diameters, and the split between the two affects the shape of that transition zone. This is a really complicated curve for us to be able to model directly. And so instead of modeling it directly, the Green-Ampt method, which is the most sophisticated of the two methods I'm going to share with you, says that we're going to have to assume the wetting front moves as a solid wave, that this transition zone is kind of neglected, and so that is one of the limitations of Green-Ampt, is that it assumes that you go from immediate transition of the initial moisture content to fully saturated. It's modeling saturated flow rather than unsaturated flow. But in spite of that, it does a pretty good job of describing the curve of declining rate of potential infiltration.
So let's just say what on the both sides represents going from partially saturated to full saturated?
Yeah, so here is fully saturated. This vertical line means that as you go down through the soil, the moisture content stays the same. And then this is the zone that hasn't been affected by the rainfall yet. So there is a zone of saturation, but then the transition zone is where there's a little bit more water than there was originally before the storm, but there is also some air in the voids. And so this is the unsaturated flow, which is associated with the transition zone. Austin?
So this is assuming that the water table is below all this, right?
Yeah, the water table would be below this and not shown. That's right.
So the line itself, like the data it's representing, is that the flow or is it like the moisture content?
It's the moisture content. Yep. Yep. And so here in Green-Ampt, it's saying unsaturated flow is too complicated. Let's throw up our arms, give up a little bit, neglect this curved region, and just try and predict how quickly the water's penetrating based on saturation. And so if we think about what's really going on, and it can be thought of in terms of the Darcy's law. Remember, Darcy's law is the hydraulic conductivity and then some cross-sectional area that the water is flowing through, and then the driving force, where H1 and H2 is some elevation gradient between the upstream and the downstream location, and then L is the length over which the flow occurs. Well, the Green-Ampt simplification says let's use those same kind of ideas. Now, instead of doing it on a volumetric basis, let's just take the area parameter out. So if we took the area parameter out of Darcy's law, then it would have units of length per time instead of units of volume per time. So if it was just K times H1 minus H2 divided by L, it would say the speed that the water is moving through the column of soil. And that's what this Green-Ampt simplification says, is it says let's measure the driving force. And the driving force is the depth of ponding at the surface, so that's H naught. That's, you can think of the water being pushed from above. And then the second term is how much the water is being pulled from below. So it's the suction. Psi is the symbol. We looked at a table of different types of soil and how much suction they have, where clay has a lot of suction, a loam would have slightly less, sand and gravelly soils have an even lower suction head. And so the more this length expands, that's going to result in a decrease of the total overall suction. When this L is very small, there's a lot of suction capacity because you've got a big depth of soil and all of it is eager to receive the water with a really high tension. So over time, as the wetting front penetrates deeper, the driving force decreases. As the length increases, then the driving force decreases, and so the infiltration rate slows down. So this lowercase f has units of centimeters per second. It's a rate or a speed, the speed that the water is moving down through the soil. If we integrate that over time, we want to know the cumulative infiltration that's occurred to a certain point, then that's uppercase F. And the way that that's modeled is just by looking at the rate of infiltration over time and integrating that from the start of the rainfall event up until T, the time in question. And this figure kind of shows both the declining rate of infiltration and then the increase in cumulative infiltration, but also it's beginning to plateau, and it'll eventually reach some maximum value that it doesn't go above. So look at the rainfall. Initially there was a pretty high rainfall intensity, then the rainfall decreased a little bit, but in each of these cases, the rate of rainfall was greater than the infiltration rate. So that means that there's going to be ponding at the surface. There's more water at the surface than can be absorbed by the soil. And the Green-Ampt simplification requires that. It won't be accurate. It'll be even less accurate than usual if we don't have ponding at the surface. So that's one of the things that I have to tell you, is that the hydrograph of rainfall needs to be above the infiltration curve for us to have any hope of accuracy. And essentially what we're seeing is a column of water penetrating down through the soil, and there's this immediate increase from the initial moisture condition to full saturation, where L is going to be, over time, the length that that water column penetrates down into the soil. So we could know what's the cumulative infiltration amount by looking at how much of the pores filled up. Like the volume of water that was absorbed is going to be the initial moisture content minus the overall porosity minus the initial moisture content. And so that's kind of like a fraction, remember, a storage fraction. So it went from fully saturated, when the water penetrates all the way down, so the porosity is totally full with water. So the physical length of this soil, like if the wetting front goes 10 centimeters, it's not that it was 10 centimeters of actual water that was infiltrated, because remember, some of this depth is occupied by solids, and there was some water there to begin with. So a 10 centimeter L does not mean that there was 10 centimeters of rainfall. 1 centimeter of rainfall may cause L to be 3 centimeters, or even more if there was a pretty high moisture content to begin with. But I just wanted to point out the difference between the penetration depth is not the same thing as how much was actually infiltrated. Just because it's a matrix of, we go back to that figure, to begin with, there is solids and some initial water. So the volume between here that's filled with air initially, that's the only place that the incoming water can go. And so if we have 1 unit of water, it's going to infiltrate much deeper than 1 unit of depth. Okay, so here's the Green-Ampt equation. And to try and make sense of it, we're going to go through a spreadsheet calculation. Remember, lowercase f gives us a rate. So that'll be the infiltration rate. And it depends on the hydraulic conductivity. It depends on some soil properties. And so psi here, the suction head, is something that we'll look up off of a soil property table. But the thing that makes this tricky is it's an implicit equation. And you remember those from hydraulics, where the unknown is both on the right side and the left side of the equation. And so here you can see when we're trying to calculate the cumulative infiltration depth, you can see that the cumulative infiltration depth is on the left side and the right side of the equation. And so our approach to that was that we made some guess of what it might be, and then we checked the right-hand side and the left-hand side, and we keep adjusting our guess until the two sides of the equation are equal. We had to do that with the Colebrook equation for friction factor F. So we'll be doing a similar thing here for Green-Ampt. We'll be using a similar approach to find out what is the infiltration depth and the infiltration amount. Now remember that the increase in moisture content, if we look at the increase in moisture content from a graphical perspective, the initial moisture content is just this theta sub I, and then saturation is the overall, where the moisture content is equal to porosity. And so this delta theta on this figure is the difference between fully saturated voids, where water is in all of the spaces, and the initial amount of moisture that was there before. And so how much the moisture increases, the delta theta goes into the equations. for both infiltration depth and infiltration rate. So we'll have to calculate that by looking at the effective saturation and the effective porosity. So the method is, in the example we're going to work, we're going to be given the hydraulic conductivity of the soil, which is a soil property that you can experiment with and determine directly. We will be given some time frame that we want to know how much infiltration was there during maybe the first 20 minutes of a storm, because we'd want to know how much runoff there was during that same period. So we'd need to look at infiltration to know what kind of runoff there was. And then we can look up the soil property of the suction head, and then the change of water content is, we're going to have to understand how much water was in the soil initially to be able to know the potential for the increase. And then we'll try some guess value of the infiltration amount on the right-hand side, and then as a starting point, you'll notice that there's two terms. There's the hydraulic conductivity times the time, and then this secondary part of the equation. So just as a guess, we might as well calculate directly K times T. And then we'll keep playing around with this guess of F sub T until the left-hand side and right-hand side are equal. Now here's the table that's in our book for Green-Ampt parameters that can be used for different types of soil. And so it has ranges of porosity as well as some typical mid-value. It's got ranges of effective porosity as well as a typical value, the suction head for these different types of soil, and then typical hydraulic conductivities. And so in the example, we'll just use these default middle values for the soil type that's described. Now if we look at the trends, if we go from sand to clay, remember what we saw in the videos, is that when there's saturation, the water moves really easily through the sand, and that's because of the high hydraulic conductivity. So for saturated flow, sand is great. But the reason when sand wasn't so great was when we had unsaturated flow. And the reason for that is, look how low the wetting front soil suction head is that the sand doesn't really draw the water in. It serves as a good conduit when there's pressure, but the sand itself doesn't suck the water downward in the same way that finer particles like clay and silty clay. With this high suction, wetting front soil suction head, that's when we saw the pretty rapid unsaturated conditions. It accounted for a rapid increase in the movement of the wetting front. So the soil suction head goes the opposite of hydraulic conductivity. It increases in the direction of sand to clay. So the clays have more suction. So the driving force is going to be the difference between the soil suction and the penetration depth, L. Now effective porosity. Let's look at effective porosity. The porosity versus the effective porosity, it's pretty close for sand, but then for clay, the porosity and the effective porosity are further apart. And the reason for that is that the clay is going to retain more water, that gravity isn't going to drain clay soils as well as it will drain sandy soils. All right, so let's try this example here. I don't think I gave you a template file. I think that we're going to have to just create this one from scratch, but there's not too many moving parts, and so that's all right. We've got a silty clay soil with these physical properties, and we want to know the infiltration depth and the infiltration rate after 1/10 of an hour and 20% of an hour, assuming initial effective saturation of 20% and continuous ponding. We'll just do some initial stuff on the whiteboard, looking at how to calculate the delta theta, and we'll also calculate the time to ponding, because we're going to need that a little bit later. Before we move into the spreadsheet, we'll calculate some of these things on the whiteboard. Okay, so first of all, the psi suction 29.22 centimeters for this soil. The hydraulic conductivity is 0.05 centimeters per hour. The initial effective saturation is 20%, so that is S sub E is 0.20. Effective porosity 0.423. I think I may have done my example at a different initial saturation. So let's change the, my calculations are based on an initial effective saturation of 45%. So please scratch that out in your notes. Okay, so S sub E is 0.45. I'm not sure why the discrepancy there, but I'm glad I caught it now rather than later. So delta theta is 1 minus S sub E times theta sub E. So that is 1 minus 0.45 times the 0.423. So that tells us that the water is going to increase 0.23265 as it goes from the initial water content to fully saturated. That's how much storage capacity the water has on a per unit volume basis. So right now, the voids are mostly, well, the space is mostly full with soil particles and existing moisture. So only 23% on a volumetric basis, 23% of that volume is available to absorb new water right now. Okay, so let's look at how much infiltration depth there is and also the infiltration rate over time. So we'll start up Excel here. Did I give you guys the template file? No, okay. Let me do that. I can make that happen fairly quick. You don't have to necessarily use it, but it'll be there if you need it. So our effective porosity was 0.423. The suction head was 29.22. The K value was 0.05. The S sub E, 0.45. And then the delta theta, 1 minus S sub E times. All right. And the example is asking what happens after 0.1 hours and 0.2 hours. So let's have 0.1 hour and 0.2 hours. We want to know what was the infiltration depth and what's the infiltration rate. I'll give you a moment in case you need to get that file. Most of you have already been able to download it. Okay, so infiltration rate. We have to start with a guess. And so it said that an initial guess might be K times T. So let's just have that as our first guess here. T times K. So here's our initial guess of the infiltration depth. Now the right-hand side of the equation that we're going to be typing in is the right-hand side of this equation. Okay, so right-hand side is K times T. So K, I'm going to anchor that so I can drag it down later, times T plus psi anchored times the delta theta, anchor that as well, times the logarithm of 1 plus, now where it refers to the f of t, we'll put in our guess value, which was in cell B10. I can't click on B10 because my formula is centered and it's getting in the way, so I'll just type in B10. Okay, and then that is divided by psi times the delta theta. I'll leave that up for a moment. Okay, now this column is the difference between the two. So the one on the left minus the one on the right, or vice versa, it doesn't matter. But the reason why it's useful to have this difference column is our objective is going to be to minimize the difference by changing this guess value of the infiltration depth. Now, you notice this note here that in some cases goal-seek may not be good enough. And the reason why is that we're working with small numbers, and goal-seek sometimes quits when convergence is just kind of like most of the way there. But solver, you can adjust the convergence criteria. You can tell it, like how many digits it has to match before it assumes the solution is finished. And so I don't know if solver is even on here. It looks like it's not turned on yet, so I may have to install that. I think it's in maybe like the options, add-ins, manage Excel add-ins, go. Okay, click solver, and then hopefully it'll show up over here. There it is. Good, good, good. So if you don't have solver, the way to get it is go to File, Options, Add-ins, go Manage Excel Add-ins, and then click Solver, yes, click OK, and then it'll show up over here. All right, so what we're going to do is start up Solver, and we want the objective is the difference is equal to a value of 0 by changing this guess value of f of t, and then click Solve. And the reason, again, why we're doing solver instead of goal-seek is we could choose these options here, and in the options you can say the precision you want for convergence. And sometimes goal-seek is okay, but in the past I've had solutions that didn't quite work out because goal-seek wasn't using a fine enough precision, whereas with solver we have direct control over that. So once we say solve, then it goes and solves for the infiltration depth.
Which cell do you change? Just one of them or both? In the solver?
Just B10, just the guess value of f of t, because everything else in here in this formula is known. What makes it implicit is the f of t. So let me put up the formula for the right-hand side again. So it's k times t. So here's the k times t. T is the only reference in here that's not anchored except for the reference also to the infiltration depth, the guess value. Anybody else also get 0.264?
Can you go through the solver again and what to put in?
Mm-hmm. Yep. All right, so we have some guess. Maybe our initial guess value was, I can't undo. Let's say it was 0.05. So there's a difference here. It doesn't work. So what we want to do is have the solver set the objective. Our objective is the difference between the left side and the right side is 0. So set objective to a value of 0 by changing this guess left-hand side of the solver. And click OK. And then keep the solution. So then the infiltration rate we can calculate directly. So the infiltration rate is going to be K times suction head times the delta theta. I guess I probably ought to anchor all these references so that when I drag it down to the next time step, it'll be useful. Divided by our infiltration depth at this point in time, plus 1. So here's our infiltration rate. Before we drag it down, let's do a reasonableness check. What we're expecting to see is a declining rate of infiltration over time. The Green-Ampt model is trying to say, over time, as those voids get filled up, the driving force is going to decrease, and so there's less tension sucking the water down from above. So the infiltration rate shortly after the storm starts should be higher than the infiltration rate later. So that's the reasonableness that we need to be on the lookout for when we solve for time step. Time is 0.2 hours. We're hoping that the infiltration rate went from relatively high to a bit lower. So let's see if that's the case by now dragging down from 0.1 hours. I just put in some guess here, 0.1. I'm going to have to, I can drag the formula down, but I'm going to have to goal seek again a second time. Okay, so let me do, again, the goal seek where I'm using solver. I guess I shouldn't call it goal seek if I'm using solver. Set the objective to the difference is equal to 0 by changing this B11, so our new infiltration depth. Click solve. Okay, so it's got more infiltration depth, and then we directly calculate the infiltration rate, and it's lower. So it matches reality. What we know from reality is that the deeper the water gets into the soil, the infiltration rate is declining. So it's a declining rate of infiltration over time during the storm. The longer the storm goes on, the water becomes less and less hungry. The soil becomes less and less hungry for the water. I guess the better way to say it is that the tension decreases as the soil column becomes saturated.
For the first calculation of infiltration depth,
Mm-hmm.
we just take the T divided by K, like that's the
Oh, the initial guess?
Yeah.
Yeah, the initial guess was just K times T.
Okay.
But we don't have to sweat it. If you put anything in there, then solver is going to eventually be able to converge. It just converges a little faster if you start with a reasonable initial guess. Are there other questions about this? Okay, so that's the Green-Ampt method. Ponding time is another factor that comes up. And remember, there's the potential rate of infiltration is high, but the rainfall rate may not be as high as the potential infiltration rate. This is important. Do you need more time to work on the spreadsheet? We can pause for a moment if you need more time on it. You got it? All right. Okay, because this is important conceptual stuff here. So just keep in mind that sometimes it's not raining as hard as the water could be absorbing, as the soil could be absorbing the water. So in other words, the infiltration capacity of the soil can be greater than the rainfall rate. And so it's not necessarily called the direct infiltration rate, it's called potential infiltration rate. And it only becomes the actual infiltration rate if there's ponding at the surface. And so we can say that when the rainfall rate is equal to the potential infiltration rate, that intersection between the two curves is when the ponding occurs. And that's when it goes from a potential infiltration rate to an actual infiltration rate, is after ponding starts. So you can see this field, when it started raining, remember the typical pattern for a storm is that at first it's just a few sprinkles. And so if it takes a while for the storm to get started, then you're not going to have the full infiltration capacity of the soil satisfied from the very beginning of the storm. Even if it's a constant rainfall rate, like this is showing a constant rainfall rate, there's still some period beforehand where the infiltration rate is greater than the rainfall rate. So if we look at it, this was in terms of rate. If we look at it in terms of depth, so capital F is depth, so the cumulative amount, the cumulative rainfall, when it comes into contact with the cumulative infiltration, that is T sub P, the time to ponding. And so you can know the time to ponding, it's the rainfall intensity I times T sub P will tell you the depth that has infiltrated at the ponding time. So this shows how to calculate T sub P. So let's do this on the board here for the example that we've just been working. The time to ponding, where we had all of these factors that are shown on the board here. The formula is going to be K psi delta theta I minus K. Now I was the the rainfall intensity. So it was 1.5 centimeters per hour. So if we have a rainfall intensity of 1.5 centimeters per hour, how long until ponding occurs? So I'm going to say I is 1.5 centimeters per hour, just constant to keep things simple. So for part A, let's find out the time until ponding occurs. So we'll just substitute in these values here. The K value is 0.05 centimeters per hour. The suction, 29.22 centimeters. And the delta theta is 0.23265. And now I, 1.5 centimeters per hour. And then the difference between I and K, 1.5 centimeters per hour minus 0.05 centimeters per hour. So you can calculate the time of ponding directly. It's 0.156 hours. So that means that with this particular soil, you'd have to have a constant rainfall intensity of 1.5 centimeters per hour for about 9 minutes. This works out to 9.4 minutes. It wouldn't be until 9.4 minutes that there's ponding at the surface. And so the total infiltration depth is going to be a little bit less than is predicted by the Green-Ampt method, because the Green-Ampt method assumes that from the beginning of the storm, there is ponding at the surface. But what this shows is that you don't have instantaneous ponding. And so one of the limitations of the Green-Ampt method, remember we talked about it's assuming that there is this constant block wave of going from initial moisture content to fully saturated. And because of that assumption, it's going to be a little bit inaccurate. And one of the inaccuracies is that it overestimates the infiltration amount because it requires initial ponding at the surface. But there's going to be some time period that it takes before the ponding occurs. So this kind of helps you to see how big the deviation is between the assumption and the reality. And the time to ponding is part of that. So what rainfall intensity would cause ponding after 20 minutes? So now, if we wanted to find out what rainfall intensity is going to cause ponding after a different amount of time, so in the first part we said 1.5 centimeters per hour. What if we don't know what the rainfall intensity is, but we know that we're talking about a T sub P of 20 minutes? So that is a third of an hour, 0.333 hours. Then I equals what in a situation like that? So the way that we can solve this is it's going to be rearranging the equation to solve for I. The same T sub P equation, but if we solve for I, then that's I squared minus I times K. On the left side, the right side is K times psi. Delta theta and T sub P. Okay, so that is 0.05 centimeters per hour for the hydraulic conductivity. Psi is 29.22 centimeters. And the delta theta is 0.23265, which we calculated at the very beginning. Now, naturally, the time of ponding of 20 minutes is going to require which intensity? So we have this known 0.333 hours down in the denominator. So this means that I squared minus I times K is 1.0207. That's the result of all of this. And so now we have an equation that we need to solve the roots for. It's going to be I squared minus 0.05I, because K is known, it's the hydraulic conductivity, minus 1.0207 equals 0. And so the roots of that equation is, one of the roots is negative 0.986, and the other is 1.036. So obviously it's the positive root, so that's centimeters per hour. It takes a rainfall intensity of 1.036 centimeters per hour would cause ponding in 20 minutes. Does that make sense with what we saw before? Well, what we saw before is that a higher intensity, 1.5 centimeters per hour, would cause ponding after 9 minutes. So this kind of does match the trend that if you have a lower intensity, that the time to ponding will be greater. And then finally, to calculate the cumulative infiltration during a certain time, we would just substitute those values into the formula for F sub t. We've already done that, so since we're running low on time, we won't do part C since we've already done a calculation similar. We've got 2 minutes till time is up for class. I want to tell you about one other method that's easier. It's a lot less sophisticated, but the Horton model just is an empirical representation of the shape of this curve, and it's based on observed behavior in different types of sand and loams and clays and so on, where you look up the minimum infiltration rate. That's what this F sub C is. It's like as low as it gets. And then the initial infiltration rate, and then tries to connect the two with a curve. So the intercept is the starting infiltration rate. F sub C is kind of like the gravity infiltration rate after all of the suction is exhausted and it's just flowing downward due to gravity. And then as a function of time is using this K value to connect the two. And so you can use the Horton model to know the infiltration rate by substituting in these given parameters, and then to find the infiltration depth as a cumulative integration of the infiltration rate, you're multiplying the initial by what time it is. I'm sorry, that F sub C is the minimum. So F sub C is the minimum, just a different formula that is used to predict the curvature of the declining rate of potential infiltration. So it's less sophisticated than Green-Ampt, but it's easier to use if you've got these soil parameters for the area of interest.
Applying the Horton example is just a matter of substituting the values that you read off of the given table into the equations. So plug and chug, as they say. So what we start with is the minimum amount of infiltration. And so for the Lee-filled loamy sand, this F sub C at a baseline is going to be 44 millimeters per hour. And then the rate of infiltration builds from there. And so this F naught minus FC is basically how far away are we at any given time from the initial infiltration rate, the difference between that initial going down to the minimum or the final infiltration rate. So you can see that when the rate constant is 0.13 inverse minutes, and we substitute in the T value of 15 minutes, then it turns out that at that particular time, after 15 minutes, then the infiltration rate at that time is going to be 78.7 millimeters per hour. And so over the long term, as that soil gets increasingly saturated, we'll see it drop even further, potentially as low as 44 millimeters per hour, whereas at the beginning, then the infiltration rate would have been much higher.
So let's think in a broad scale. Like for a catchment like this, in a large hydrologic model, what we're trying to address is where's the water coming from, where's it going, how much of both. And so in other words, it's a mass balance question. And this is a model for the outflow from a large watershed that if you're looking at all of the main factors that account for the water in and the water out, then this will enable you to predict the discharge from a big watershed. And I did some work for the Division of Environmental Protection here in West Virginia. A couple of years ago, they had some chemical companies who were interested in using water. And the DEP had to determine how much water can people extract from a river and still leave enough for to maintain the habitat for fish and to make sure that there isn't any damage. And so what we had to do is we had to look at the whole spectrum of each one of these input parameters to find out what's the combination of worst case scenarios to see for a certain discharge, how often would you be taking out too much water. So for this basin, just think about the river where water is coming out of a basin. Now, some watersheds have inflows to them, which means there may be a river that's coming into a watershed. So this image is showing that the watershed in question just is bounded by a ridgeline on all sides. And so this illustration wouldn't necessarily have a surface stream coming in, but sometimes we define watersheds so that there is a stream coming in. So of course, if we wanted to find the flow rate out, you'd have to account for the flow rate that was coming in. The rest of the mass balance is that water is going to be entering the watershed as precipitation, of course. It's going to be leaving the watershed as evapotranspiration, and so that's the combined effect of evaporation from the surface of water, evaporation from soil, and then transpiration from plants, where the plants are maybe taking water from the soil and breathing it out to the atmosphere, discharging water vapor. You'll notice here that we're saying groundwater recharge, and here in the definition it's both a plus and a minus, because depending on the conditions, it may be that during a dry period you have water in the subsurface that's gradually coming towards the surface and feeding the base flow of streams. And so during some parts of the year, the groundwater recharge may be contributing to the discharge out of an outlet, but then there are other times, like during periods of heavy infiltration, that actually the water is going into the soil so that there is a net increase in the amount of moisture underneath the surface. And so groundwater recharge can be positive or negative depending on the preceding storms, and also depending on how slowly the water moves through the subsurface. So if you ever go hiking around in the woods, you'll notice that there's still a little bit of water in the stream even weeks and weeks after it's rained. And that's because water is going to be seeping out of the soil into the low points in the watershed, because it takes so long for water to go through the subsurface, especially when there's a lot of clay and silt in the soil like there is here in West Virginia. Now, the same thing is true about surface water storage, that it can either be positive or negative. So if we have a lake or a pond inside of this watershed, it might be that the pond is filling up, and so that's going to be reducing the amount of water that's available for outflow. Or it could be that water is being released from the pond or the lake. And so that kind of a release would increase the amount of water that's in the river compared to other times. Now, the last two terms have to do with kind of the human uses inside the watershed. And so LQ means large quantity user consumption, and that could be a power plant. And of course, a lot of water is used to cool down in a power plant generating steam. In chemical factories, they're using water for cooling. And so those are examples of large quantity users. There are some places where they bottle water, and that actually accounts for quite a bit of the water inside of a watershed, like if Dasani or if there's a Coca-Cola bottler in an area, then that can consume a lot of water. And then the other thing is the agricultural uses. Now, here in West Virginia, agricultural uses are a very tiny fraction of the water that's going in and coming out of a watershed. But in places like California, that can be a huge effect, where the agricultural uses is actually the majority of the water that's going in or out. So this is the large-scale hydrologic model, and what we're going to try and do is predict the outflow from a watershed by accounting for each of these terms. Some of them in the short term, like over the course of hours, there's not going to be very much evapotranspiration. Like the critical events that we're trying to predict would be a storm. You know, how much water is coming out of the watershed during a storm. And so during one of those big events where there's a lot of precipitation, then the change in storage will be important. But the relative contribution of large quantity users and of agricultural uses, these become less important on the short term. It's really only in the long term that some of these factors play an important role. So let's talk about some of the background of these different terms. Abstraction is a phrase that's used in hydrology to describe the initial difference between when you observe rainfall and something that's known as rainfall excess. So precipitation and precipitation excess, or rainfall and rainfall excess, the difference there is that before water can begin to flow over the surface of maybe pavement or over grass, anytime the water, before it can move, it has to wet different surfaces down. You can see here is, it looks like maybe some sort of tiles, and there's a puddle there. And before the water is going to flow sideways, there has to be a certain depth in the on the tiles. And the same thing with this roadway surface. Right now it's kind of glistening, and that allows you to see the texture, but it's a porous surface, and each one of those pores has to be filled before there's any movement of the water sideways. And so abstraction is just referring to any sort of a change in the timing or the quantity of water prior to it being able to contribute to peak flow. So abstraction has an effect of delaying the movement of water and reducing the quantity. And how much abstraction you have in a watershed is going to affect the conduits that you have to size to convey stormwater flows, and specifically the intensity is going to be delayed by the abstraction. And we usually quantify abstraction by a depth. Like we'll say that you know, if we're going to have an inch of rain onto this asphalt, maybe the asphalt uses 2/10 of the inch. We're going to set that aside for abstraction. And so then the rainfall excess would be the rainfall of 1 inch minus the abstraction of 2/10 of an inch. And so what would be left over to actually contribute to peak flows would be the 8/10 of an inch. And so it delays and it also reduces the quantity. It also is going to affect, if you've got a watershed with a lot of abstractions, that may change the sizing of ponds. It's going to mean that less water has to be treated if you have stormwater treatment. So it's an important factor, although usually it's only a small percentage of the rainfall. If the storm is getting towards the design storm, then abstraction gets filled up pretty quickly. During a 5 or a 10-year storm, the abstraction is just going to be a small part of that. But during smaller storms, you may not even have enough rainfall to satisfy the abstraction. So sometimes if it's just sprinkling rain out, you know, we talk about how bad the drainage is here in Huntington and how Fifth Avenue fills up with water and it's kind of like driving through a river. But on a day where it's just sprinkling rain, there isn't any water going through the gutters and there's no flow to the pipes because it didn't even get the concrete all the way wet in just a sprinkling. And so you can kind of get a feel for that there's a certain threshold of water that doesn't generate any peak flow. There's no runoff until the abstraction is satisfied. Interception is related to abstraction, and what interception is where vegetation or buildings are preventing the rainfall from even getting to the ground in the first place. And so interception precedes abstraction. And different types of plants can intercept different quantities of water. You can see here in this image that we have a leaf and it's kind of just holding on to a raindrop. And so depending on how tall that plant was and how much leaf area there is, you can get a feel for, you know, the ground underneath this plant may be receiving considerably less rainfall than is actually coming from above. And so you think about the path that a raindrop has to take to get down to the ground, and on average, how many of these leaves is it going to encounter on the way down? Now, certain trees have a lot more leaf area than others, you know, like evergreen trees that just have really thin pine needles may account for less interception than oak trees, which have a broad leaf area and lots of height and several different layers to the canopy. And so there have been lots of studies in the past where they've studied different varieties of trees and looked at the seasonal variation of interception. Now, this percent interception is going to change depending on the storm size, and so this is just maybe a little bit oversimplifying, because if you had a 100-year storm, then it's likely that you'd see a lower percentage interception than if you have a 2-year storm. So I don't specifically know on this table what kind of storm intensity they were looking at, but it is a relative comparison, and it shows you that for example, if you have, mixed tropical forests in the summer, they'd only have 16% interception, which is kind of a surprise that it wouldn't be higher than that. But in the summer months, for deciduous hardwoods like we have around here in West Virginia, most of our trees are hardwoods like oak, for example. The summer months, there's a lot more interception than there is during the winter months. But there's still, just because of the branches, the wood itself plays a role in interception. The local climate can have an effect on interception as well. Like if the leaf is already relatively coated with like a mist, because of really foggy conditions, and that can reduce the amount of interception. And the density of the vegetation inside of, if it's just a single tree or if it's a tree that's surrounded on all sides by other trees, then that could change the interception above or below the values that are shown on the table. And of course, the age and the size and the health of the vegetation. You know, a relatively new tree that isn't as tall is going to intercept less water than a really large, mature tree that's a lot older. One of the formulas, the empirical formulas that's in your book that allows you to estimate the interception is shown here on the screen. And what you do to apply this is you start off with a storage quantity, S, depending on the species of the tree. And then you look at the amount of rainfall, and this is not an intensity, this is an overall amount. And so you can find out how much interception there is by accounting for the difference between the precipitation and the storage, but then also accounting for what sort of evaporation may have occurred during the storm event. And we're kind of, this is like best case scenario, that you're going to have enough time during a storm event that there will be evaporation. And so you're calculating the maximum interception that you could potentially see when you're using this formula. But let's just give it a try, see what the calculations are like. If we have a 1.5 hour long storm and we have 3.8 centimeters of precipitation, and we are able to calculate the evaporation amount during the storm is 0.3 millimeters per hour. Now, spruce trees with a leaf area index of 6.5, that is going to be going into the K value, the leaf area index. That is basically meaning that if you're looking down on the tree from above, there's 6.5 layers of leaves from the top to the bottom. So, you know, if you know, a tree, when you're looking at it from above, is circular, then essentially there's 6 times as much area, surface area on the tree as there is top view area, just looking at the projection of the tree. So let's find out of the 3.8 centimeters, how much of it is available for runoff and infiltration. In other words, the precipitation minus the interception. What's the difference between the two? What's the leftover quantity? So the time period in question is 1.5 hours. The precipitation quantity is 38 millimeters. The evaporation is 0.3 millimeters per hour. And then the leaf area index of 6.5. So the interception is going to be, first of all, the storage times 1 minus e to the minus p divided by s plus k times e times t. Okay, so the storage is 7 millimeters. And the question is, during a 1-hour storm, how much of that storage is filled up? That storage is a maximum potential. And so it could be that this 1.5-hour storm didn't fill it all the way. So 7 millimeters is the maximum storage. In our case, it's 1 minus e to the negative 38 divided by 7. And so there's 38 millimeters of precipitation out of 7 that can be stored. Inside this parentheses, that factor is going to be pretty close to 1, as we'll see in just a bit. But the plus 6.5, the leaf area index, times the evaporation rate of 0.3 millimeters per hour, and 1.5 hours. Okay, so evaporation during the storm event, there's going to be 2.925 millimeters of evaporation, and then storage by the leaves is going to be 6.969 millimeters. So most of the overall possible storage has occurred. 7 millimeters is the maximum, and we gradually approach that maximum depending on how much it's rained. Because there's always going to be some precipitation that maybe it's a leaf that's not flat. That's what this is trying to account for. Is it's not like the tree gets fully saturated and then it starts pouring at the same exact rate. Even when you're standing under a tree during a rainstorm, you'll definitely stay drier, but it's not like none of the raindrops get through there at the beginning. They gradually increase the amount that can penetrate down through the canopy. But the sum of these two components, the interception is going to be 9.89 millimeters. And so the precipitation amount was 38 millimeters. So the runoff and infiltration is 28.11 millimeters. So it's just going to be the difference between the precipitation that occurred and then the interception by the tree. So we'd call that the rainfall excess. So the 28.11, another word for that is rainfall excess. So I heard some whispering as I was writing on the board. Is there any questions about the example? No? Now keep in mind, this is just an empirical equation that's kind of doing its best to represent what's observed. So is it always going to behave exactly this way? No. But it's a method for trying to predict the effect that interception has. And so rainfall and rainfall excess aren't always the same thing. The interception can have a pretty big effect, especially if the precipitation quantity is relatively low. Okay, so what are the other things that have to be satisfied before the runoff occurs? Well, one of them is depression storage has to be filled up. And in any kind of a regular watershed, if we go back to the watershed, there may be low points in the watershed that they're not necessarily ponds, but they could just be places where puddles are going to accumulate. And all of that puddle area has to be filled up with water before there's going to be any lateral movement of the water through the watershed. And so that is what depression storage is. You can see here is a little bit of a roadway path, and here's just a puddle of water. And that's going to promote infiltration down into the soil, of course. And so this is just temporary storage at the surface. Over the long term, it'll either evaporate or it'll infiltrate. But in the short term, it's going to reduce the amount of water that is being transported towards the outlet. So we kind of have to account for the irregularity of the surface and estimate how much water might be stored inside of a watershed. Okay, this image is showing an airplane on a runway, and runways, for obvious reasons, are pretty flat, and so they don't want to have too much of an angle to a road, to a runway. Like in contrast to, I was noticing Fifth Avenue. I was in the left lane as I was going on Fifth Avenue, and I was kind of like, you're really leaning over sideways. It's a struggle to drive uphill and to go straight, so they just keep putting more and more pavement and then having to, that angle increases. But the point is that this is really flat, and so the overland flow and the sheet flow is going to be a lot slower on like a runway than it would on a road. And so there's going to be relatively more depression storage on a flat surface. And so depression storage, the kind of trend that we could see is that the flatter the slope, the more storage there is, even just on a on a flat surface like pavement or concrete. And so a steep pavement would maybe only hold on to 1/2 millimeter of precipitation, whereas if it's flat, it could be triple or even 7 times as high. Impervious areas are going to be not necessarily paved, but it could be locations that have more clay in the soil, and so the depression storage is going to be a little bit lower. Compared to lawns, the high depression storage there is related to just the surface area of the debris at the surface. So forest litter means like broken off twigs and branches and leaves and maybe grass clippings and dead decaying vegetation. And so there can be quite a lot of precipitation onto a heavy forest litter before there will be any movement sideways through the watershed towards the outlet. Now all of this is going to be variable depending on the slope of the watershed and the specific surface area, meaning the surface area relative to the plan view area, and you can think of that kind of as a porosity of the materials at the surface. In the same way that when we think about the porosity of soil, it is taking into account the voids relative to the overall volume. The specific surface area has to do with how, if you've got lots of different layers of leaves between the top and the bottom, then each one of those outside areas has to become wetted before the water will make it to the bottom and start flowing laterally. And then, of course, the previous recent rainfall events is going to have a huge effect on whether the depression storage is already wet before a rainfall event occurs. So the reason why we've been talking about these is that these are all factors that play into the response of a watershed to a rainfall event. So the stream response. That's what we're going to try and predict with the watershed modeling software. Is the hydrograph is a function of time. And we care about that because it will tell us how much water is available to be consumed if we're thinking of water as a resource rather than as a nuisance. But sometimes the water isn't a resource. Sometimes water is just something that has to be disposed of because otherwise it's going to cause damage. And even when we're thinking of water that way, it's really important to study and understand the stream response because it allows us to predict when floods are going to occur, and it allows us to plan for those by putting things like the floodgates into, we've got flood walls here in Huntington, and they have to have some advance notice to be able to put those gates on before the river rises pretty high. It also has some implications having to do with water quality, and you've probably noticed if you've looked at the Ohio River that it changes colors as much as it changes height. And when it's been raining a lot, it kind of turns a brownish color. And the reason for that is that, coincident with really high flows through streams is that it's able to scour more turbulent, more sediment, and so there's a lot more scour of like the soil particles, and then those soil particles become suspended in the water, and you can almost taste it in the water that we get from the tap here. That maybe it's just my mind playing tricks on me, but I seem to think that the taste of the water changes when the source is brown because they're having to add more coagulants. They, here in Huntington, have the ability to add powdered carbon to the water because when there's a lot of heavy rains, then it's going to take the pesticides and the fertilizers that farmers use in agricultural areas. And so when there's a lot of peak flooding into the river, then it decreases the water quality, and they have to kind of change their treatment that they're using here. How many of you have been to the treatment plant? None of you? I think probably you'll get a chance. I think Dr. Yoon usually takes people over to the treatment plant here in Huntington. At least he did last year. And they'll show you where they put in the powdered carbon to try and absorb some of the pesticides that get into the river during really stormy times. So part of the importance of understanding stream response is it allows people who are using the water or who are trying to divert the water to plan their operations and understand when they're going to have to maybe change the treatment system. Okay, so a hydrograph is a graphical representation of the input to the watershed. And so it's going to be rainfall, or if we're already able to subtract out the interception, and then this would be the rainfall excess. We can do a hydrograph of either one. We can have a hydrograph of rainfall or a hydrograph of rainfall excess. Now the outflow from a watershed, that graphical representation is a hydrograph. So hydrograph is rainfall, hydrograph is runoff. And it's a graphical representation of discharge versus time. And so here you can see that the time axis is the same for both of these, but the rainfall is always going to be a little bit before the runoff. And so the difference between the two, the difference between the rainfall and the runoff, is the travel time, and it's how long it takes to satisfy the initial abstractions like surface storage and wetting of the leaf area and so on. There's a lot of factors that affect the difference in time between the two. There's a lot of factors that affect how big the peak is going to be. And so let's talk about some of the physical factors. Of course, the precipitation characteristics is going to play a huge role, because the more rainfall you're going to get, you can expect that there's going to be more runoff. And of course, the direction of the rainfall is also going to play a role. You know, if it starts raining at the tail end of a watershed, like far away from the outlet, and it's only on a portion of the watershed, then there's going to be more travel time than if it has rained everywhere on the watershed equally. So when we talk about precipitation characteristics, we're not just talking about the amount, we're also talking about where in the watershed the rainfall is, and then maybe even the direction that the precipitation is moving during the storm. The watershed characteristics can include all sorts of things like the soil types, the land use inside of the watershed, and it can even be things like the stream characteristics. Here, this is showing relatively straight streams. And if the streams are relatively straight, then it might be that the water is able to move through the watershed more quickly than if the streams are meandering. And so the sinuosity and the flow path that the water has to take between when the raindrop hits the ground and when it gets to the outlet, that's going to have an effect on the stream response as well. So this representation is kind of making the point that you'll notice that the streams are getting wider as you move in the direction of water movement, and that's because at each point the contributing area increased. So the stream is relatively narrow here because just conceptually, you know, streams don't actually look as perfectly triangular as this, but the concept here is that you have overland flow, and then there's a certain point where you've got enough overland flow that now it's channelized flow. And the channel gets progressively bigger and bigger as there's more water that's being conveyed, and so that's why this flow path is getting wider. And then you have several little streams contributing to a much larger stream. And so these lateral inflows are contributing to the increasing volume that's observed in the stream. And maybe at a certain location of interest, that's where we're either gauging the stream or we have a crossing, and that's where we have to determine the peak flow rate to size a culvert or a bridge or something like that. So the book shows several different topographic patterns that contribute to how the water moves through the watershed. And dendritic patterns is what we see in this area, where there's, relatively speaking, a uniform erosion resistance. And so it's just kind of the streams going from left to right are no more probable than streams that are going up and down. But depending on rock fracture mechanics and where there maybe are plates coming together, other geographic factors. There can be other types, like a rectangular flow pattern where it looks like there's a much lower probability of streams going sideways. It's just the flows are kind of at right angles, and those are characterized of watersheds where there's rocks rather than soil that's uniformly eroding. Rocks break in consistent directions rather than eroding uniformly. The trellis patterns may be where there is unequal resistance to erosion, and so if you had a ridge line, that's usually what we'd see here, is that there's no streams because there's a ridge line there. And it may be that there's a ridge line there because it's rock in one part but soil in the rest. So if you have interspersed regions of bands of rock and then bands of soil, the soil would be eroding but the rock would be staying, or maybe it's different types of soil. Like if you have a higher strength soil that's more resistant to erosion, then there can be, because of unequal erosion, just certain directions that the water seems to be moving. And then trellis patterns would sometimes be seen in a coastal plain, like on the east coast in the lowlands of South Carolina, for example, where there's unequal erosion resistance. The flow path is going to be longest in the dendritic pattern. The water traveling from one spot to another is the slowest in the dendritic pattern. But then the flip side of that is that you can have relatively steep watersheds in a dendritic pattern as well. So one of the factors that you can use the computer to calculate is the watershed slope. And the computer is really good at looking at the elevation map that you'll feed into the computer. In the background, it's going to know the elevation of every point in the watershed, and it can compare elevations of adjacent pixels and calculate the average percent slope. And one of the things that's really extreme in West Virginia is we'll see watershed slopes that are routinely in excess of 40%, where outside of West Virginia, I don't know of any other state that has such consistently high watershed slopes. And so although we have these dendritic patterns, which you think maybe that's going to slow down the movement of water, what speeds things up and makes things so flashy here in the state is the fact that we have really steep watershed slopes. Stream ordering is just meant to show that there's an interconnected network of streams, and in fact this network may look different during wet areas than it does during dry periods. But we'll get into that in just a minute. A first order stream is a stream that doesn't branch any further, and so you can see here the basin order, the ordering is numbered. So a first order stream doesn't have any upstream branches. A second order stream receives only first order segments. And then when we finally have multiple second order streams coming together, that becomes a third order stream. Other ways to classify streams is whether there's always water in them, and that's what we call a perennial stream, something that always continuously is going to have flow, and it will continuously have flow because it's getting some groundwater in there. A perennial stream has a big contribution of the base flow being groundwater, and that's why it continues to have water even during dry periods. A perennial stream can also be something with just a lot of upstream area. Intermittent streams are the ones that only have flow during the wet season, and then an ephemeral stream is one that only has flow in it like in the period just immediately during or after a storm. So here's a picture of a perennial stream. This is the Provo River, which is kind of famous for trout fishing. An intermittent stream where we're not going to see water except for during a rainy season. And then an ephemeral stream. This one is a ditch that's only going to receive water in the moments immediately after a rainfall event. This is the same watershed, but during a dry period on the left and during a wet period on the right. And what you can see is that the reach of the stream extends during the wet period. And so the solid black line shows where there's actually water that's flowing, And during a dry period, there's going to be these areas of seepage where the water is coming out from the groundwater, kind of a wet spot on the side of the hill that feeds into the stream. But during a wet period, the flowing water extends much further into the watershed, and the location of the seepage is shifted upstream as well. So there's going to be more seepage in a greater variety of places during wet weather. And then there's also, because of just the surface, the flow at the surface, then the flowing stream extends upstream during the wet weather. Watersheds can be nested inside of other watersheds. And what this next series of images is going to show is for progressively smaller watersheds how the stream response changes. And so in this first one, we're looking at a drainage area of 0.2 miles. And so that's a small watershed. 0.2 miles is pretty small. And because it's so small, the response of the runoff is very closely tied to the precipitation pulses. And so you can see that here in the hydrograph, there was this initial burst of rain, and that's what caused this first peak. And then there was relatively nothing going on, and so it started tapering down, and then there was another pulse of rainfall. And so that rainfall pulse is what caused this peak. And then it starts tapering down again, and there's a third pulse of rainfall, and that's what causes this peak. And so in a small drainage area, there's a pretty close relationship between the rainfall intensity and the runoff flow rate. But if we, and this is, by the way, if we are just zooming in on a really small portion of a watershed inside of the state of Illinois. So this is a figure in your book that's saying within Illinois, there's this watershed inside of the state. And so this is the overall watershed, but some tiny little portion of it that's only 0.2 miles is going to have a pretty close relationship between the rainfall and the runoff. But now if we extend that area and look at a greater contributing area, so now we're looking at 3.2 square miles instead of 0.2, then these peaks kind of smear together. And also they're later. It takes more time for the rainfall to get towards the outlet. And so you'll notice that the peaks are further to the right, and the relative height is smaller than it was before. And it's not that the absolute quantity is less, because that's not the case, but there's going to be just essentially a more muted response because of an effect called routing. And routing is how long it takes to move the water through the watershed. And if you think about, if you had a bucket of water and you pour the water into a really long trough, when you pour the water in, if you're able to pour the entire bucket of water in just 1 second at the head end of a trough, then we could look at a graph of quantity versus time, and it would be essentially a big pulse. So here we have a long channel, and you have a bucket of water, and you just pour it in all at once. And so it would look like all of the water is in there at, this is maybe distance, and this is amount. So the bulk of the water is basically all together. But then think about, there's some water in here, and the water that's on top is able to flow downhill at a faster speed than the water that's in immediate contact with the channel bottom. And that's because of the no-slip condition and friction. And so what that causes to happen is, as we move downstream, the amount of water kind of spreads out, where instead of being all together as it was in the head end, by the time we get down to here, maybe the water is kind of like this. And then eventually, when we get to the end, it is spread out even more. So this effect is called routing, and it's just the effect on amount and timing that occurs as water travels through a channel. And so what we're seeing here is that as we look at progressively larger portions of this watershed, now we have a drainage area of 16.6 square miles, we don't even see the individual peaks anymore. And because it's a wider area, the time to peak has shifted further to the right. And finally, when we look at the entire watershed as a whole, 43 square miles, then it's the furthest to the right and the longest period of time until the peak. So the flow mechanisms, overland flow is going to be wetting at the surface that makes its way to a channel. And as the water is flowing over the surface, of course, there's also some infiltration that's occurring. And so you'll notice here this figure is showing a wetting front that's going progressively deeper into the soil. But there is some quantity of water that arrives at the surface due to rainfall and flows over the surface towards the channel, and that's the fastest. Saturation overland flow is where the saturation from below, basically as you fill up the voids in the subsurface, then the base flow into the channel is going to increase, because there's always water that's seeping into the channel from the subsurface, and so it's increasing the amount of groundwater movement. So this figure shows that, as it rains, the water table increases, and then more water makes it into the stream than otherwise would have before the storm occurred. So Hortonian overland flow is fast, but the saturation overland flow is a little bit slower. And it seems kind of strange that they call it overland flow, but the point is that it's a lot faster than just the base flow that takes many days after a storm event to continue draining out of the soil. You push the rain in here, and some of it comes out faster downstream. It's not necessarily the same exact particle. It's just by raising the water table on one side, it exits more quickly at the other. So I guess that's why they're calling it overland flow, is not necessarily because it is directly flowing over the surface, but because of the speed of it being relatively quick. Now you'll also notice that some of the seepage exits at the surface rather than exiting into the stream directly. So before the water table raised, none of it was coming out at the surface, but now it is exiting at the surface. Base flow is the water that's in a channel even during dry weather. So it's groundwater that's contributing to the flow in the channel. Return flow was the infiltrated water that reemerges at the surface. And then during wet weather, this is another way of seeing the saturation overland flow and the increase in the base flow because the water table is higher. Okay, we can see the effect of these different components on a hydrograph, and even before a storm starts, there's going to be some flow in the stream, and that's the base flow. That's the water that's inside of the channel during the dry weather. And then once the rainfall event occurs and there's this rising limb, then the saturated overland flow is what's contributing to that rising limb. And the inner flow is kind of the lateral motion of the water, so it's in the zone of aeration where it's not fully saturated yet. So it's kind of as the voids begin to drain out before you get back to the base flow at any particular time. Now we're going to talk about a lot of different factors out there in the watershed that can affect the shape of the hydrograph, and it's related to what direction the rainfall is going in. It can be things that what portion of a watershed the storm is falling in, the shape of the terrain out in the watershed. And so there's a phrase that's in your book that I think is really telling in the way that you should understand what abstractions are. So let me give you a moment to read that phrase. If you haven't already read it in the book, then now will be a chance to read it here up on the screen. All right, so it's making the point that when the abstractions have been accomplished, and I thought that's kind of a strange use of words, but in a way it kind of tells you what the abstractions are doing, is it's all these little reservoirs that have to be filled inside of the watershed before water begins to flow overland. And so we're talking about the wetting of the leaves, the wetting of the branches, the wetting of the litter, the forest litter, or whatever it is at the surface, the filling of all the surface storage ponds and so on. And so once all those abstractions have been accomplished, as it's saying here, then the water starts to flow overland. So the hydrograph shape is affected by factors like the size of the drainage area. And we saw that in last time's lecture, where if you have a really large drainage area, remember that the hydrograph response is more muted compared to a small watershed area. If you have a really small watershed area, then that reduces the travel times so that a big burst of rainfall can have their very flashy response. You're going to see a flash flood from a small watershed, whereas in a large watershed, by the time the water has traveled so long, there's a lot more of that routing effect. Remember, we discussed the routing effect is kind of like pouring a big pulse of water into a channel and how it spreads out because of the friction that it encounters in its journey. Channel slope plays a role in the routing, and there's going to be more of a dissipation of a pulse of flow if a channel slope is relatively flat. There's going to be less dissipation of a pulse if you have a steep channel. Hydraulic roughness plays a similar role, where the smoother the surface is compared to a really rough surface, then the smooth surface isn't going to delay the flow, and they're going to have more of a distinct peak compared to the roughness that would be slowing it down. Storage inside of the channel, there can be like pools inside of a channel that have to be filled, and that would be contributing to a delay in the same way that if there are puddles inside the watershed itself. And of course, the length of the stream is kind of akin to more travel time before it gets to a point of interest and more spreading out of that normal distribution. There's other things as well, like channel density. And if you have a lot of streams inside of a watershed, then the water doesn't have to travel over the surface as long before it enters those channels. And water flows through channels a lot more quickly than it does over the surface. And so if there's a really long overland flow until it gets to a channel, then that might make for more delay and less of a peak, compared to lots of channel density means it's getting into that high-speed network towards the outlet more quickly, and then there would be a more flashy, quick response. Of course, you already know that antecedent moisture conditions are talking about the rains in the time prior to our storm of interest. And so if the watershed has already had lots of rainy weather and all the abstractions were accomplished yesterday and the day before and the day before that, then the stream response is going to be more immediate than if all of those abstractions had to be accomplished with the storm that we're focusing on now. Of course, you already know that things like vegetation can slow down the movement of water, and if we make channel modifications, that can go both ways. Sometimes channels can be modified to make them more straight, and then the water is conveyed more efficiently, and then that would increase flashiness. But increasingly, organizations are doing all that they can to make the channel conditions more like they were naturally, because the natural undisturbed stream is the one that's going to be the most stable over time. And so sometimes these straight channels are made to be meandering again, and they're trying to put in like a rough riprap along the sides of channel banks to reduce the probability of scour, and that increases the roughness, and then that will delay the peak flow. So what we're going to do is go through some of these effects and look at the effect that it has on the hydrograph. I really like these sketches a lot. And the reason why I mention it is that there's a good chance I'd maybe ask you to kind of like regurgitate sketches like this in a quiz or in an exam to show that you understand the underlying concepts. And so it's definitely not something you should memorize, but in each case you should be able to understand like what is the phenomenon, what is the force that's causing, like for instance here, slope to change the hydrograph. And so what we're seeing for a gentle slope is that because the water is traveling more slowly over this slope, that the hydrograph is going to have a more muted shape than a really steep slope. And now why is that? Because remember that when the flow arrives more quickly, then the hydrograph peak is higher, and there's less time for diffusion up and downstream. So a steep slope means the travel times are slower, and if the travel times are slower, the peak arrives sooner. So you should be able to reason through and explain, like, why does the slope have this effect? And you should also be able to remember a steeper slope compared to a gentler slope. You know, if I said, here is the hydrograph for a gentle slope that's not very steep, how would the hydrograph change if it was instead a steeper slope? Well, then what you'd do is you'd shift it to the left and make the peak higher. Okay, let's look at the effect of hydraulic roughness. And so what the sketch is showing is a relatively smooth surface that's less rough compared to a more rough surface. And so then ask, does this match what we'd expect? How does the hydraulic roughness either delay the flow in the case of a lot of roughness? So there's a lot of roughness there. The water is experiencing lots of friction, and so the velocity is going to be slower. And so if the water is moving with a slower velocity, some of the water is going to be trapped down here in the cracks of the whatever the roughness is in the pores, whereas when it's less rough and there's more smoothness there, then a smaller fraction of the flow is going to be in contact with that bottom layer. More of it is going to be up top with a higher velocity profile, and so just overall it's moving more quickly in the less rough channel than in the more rough channel. Okay, storage. In some ways the storage is a little bit like the roughness, because you can kind of visualize that there are little pools in each of these boulders. Between the boulders, that's effectively a storage pool that has to be filled up before there's flow on top of that storage pool. So it's partly a roughness effect and partly a storage effect. But just in the case of the storage itself, this is something that we've seen before as a best management practice to try and reduce the effects of urbanization. Yeah?
I see that it would cause like a large delay.
Mm-hmm.
Once it overtops it, how does it slow it down? Or is it just like the roughness of the water bubble?
It's because some of the water remains in these pools. And so if we're talking about the overall volume of water, if there's little storage, then after the pulse has been through, the surface may still be wet, but the bulk of the water is arriving at the destination kind of like in a more concentrated way, whereas it's shifting it to the right because of the delay, but then the peak is lower because the water is going to seep out of this storage more slowly. So it's not like it's not that one storage is filled and then it all goes to the next one and then it's empty. It's kind of like a chain where each of these pools is going to kind of drain slowly. That's right. Yeah, there is a storm that could fill each of those pools so quickly that maybe it would have an irrelevant effect. It would be a little bit lower. But yeah, there is a scale that every kind of effect we're talking about, there's a storm big enough that maybe we wouldn't be able to see the difference between this gentle and steep slope. There's some big enough storm that maybe we wouldn't notice the difference between less rough and more rough. So each one of these could be overwhelmed by just like that 500-year storm. But I mean, as a general trend, the more storage you have en route between the watershed and its destination, the delay and the reduced peak is what you'll observe.
I know like this is the idea of dams, but like what's a smaller scale of this happening in real life?
It would just be a channel that isn't going downhill at a uniform slope. So in a regular slope channel, and that's how most natural channels are. If you go up in the mountains, you'll notice, you know, they just kind of are irregular in their downhill. And so, you know, this little pool is going to be filled here, and then this little pool is going to fill here. And so the irregularity of the slope, you know, we're talking partly about gentler versus steeper, but then this would have a lot more storage, even though it's going from point A to point B. If there was a similar channel that had the same slope, and so it's not so much that it's not as steep, it's just that it's less irregular, then there wouldn't be the same amount of storage in there. So that's a great question. It can just be natural features, and here it's meant to look engineered, but it doesn't necessarily have to be something that's inbuilt. It could just be the characteristics of the stream itself. And you know, that goes to what has the stream got in it. Is it going to be sand and like silt? Well, you're probably not going to see a lot of irregularity due to sand and silt. When you see a lot of irregularity, it's because of rocks, like the differential scour and movement of rocks. Like if you got a big boulder here, and then like some smaller gravel there that was moved downstream. And so you see that like in the New River, there's a lot of irregularity to the channel slope in some spots. And that's why, you know, people are rafting there, is because it's the rocks that cause those big drops. The sudden drops in elevation is what gives you the rapids that are kind of exciting. I went whitewater rafting this summer, and we got tossed out. Our boat was upside down on top of us. And this is one of the rapids where the guide says, if you get tossed out, you got to get in the boat quick, because then there's more rapids downstream. So it was exciting. That's why it's fresh in my mind. So yeah, those features, as they call them, are because the rocks give irregularity to the channel slope. Whereas you're not going to see that in the mud river. Nobody is whitewater rafting in the mud river, right? It's because it's just mud. The channel is pretty uniform, it's pretty gentle, but if you've got rocks and steeper slopes, then there's more potential for storage, and more potential for recreational excitement. All right. So drainage density is where we're talking about there being a lot of streams draining a network, a watershed. So if I draw like a little watershed here, a low drainage density would be just like there's a main channel and maybe a couple of branches. And so if we have a low drainage density, then it's going to take longer for all of the water to make its way towards the outlet, because, you know, this raindrop has to flow over land, which is slow, before it finally gets into this high-speed network that it can travel with a more rapid way. But high density means we have lots of little tributaries that extend into the network, and so any particular raindrop is going to be able to jump into a channel more quickly than it otherwise would. So that's the relative effect. Is high density means higher peaks that arrive sooner, low drainage density, lower peaks that arrive more slowly. And finally, channel length. They haven't made this very obvious, but a shorter length channel, higher peak that arrives sooner, longer length channel. I guess the reason why they haven't made it like that dramatic is that once it gets in the channel, the flow is pretty fast. And so like the real delay is in overland flow. You know, that's like if we look at the travel time in most watersheds, Once the water gets into a channel, it's just going to be a series of minutes. Whereas when the water is flowing over the land, it's a much longer time. And so I guess the reason why these two peaks look pretty much the same, it's kind of a more subtle difference, is they're going after the fact is, shorter length is going to mean it arrives sooner and it's a little bit higher, but relatively speaking, the difference is less dramatic than cases like the drainage density, where the main difference arises because of an increase in overland flow time. Are there any other questions about these effects? Okay, now the timing of the rainfall can have an effect on the hydrograph shape. So compare these two storms. The storm on the left, most of the water arrived early, whereas the storm on the right, there was a little bit of rainfall and then the majority of the precipitation occurred late. And so what you can see is that the stream response is directly related to the rainfall. When the rainfall is front-loaded, the peak comes early. When the rainfall is later, then of course the peak comes later as well. So sometimes you'll look at flow data in a watershed and the hydrograph looks different from some storm that you were looking at months or years earlier, and you wonder, like, why does the hydrograph look so different? In the 24-hour period, they were both 3-inch storms, but then it's often because you may have daily precipitation data, but the 3-inch storm from last year could have been completely different from the 3-inch storm this year. Last year's storm could have been one where of that 3 inches, most of it was in the morning, whereas this year's storm, maybe the 3 inches was mostly in the afternoon. And so the stream response could be dramatically different just because of the temporal distribution. So temporal distribution means the variety in amount over time. Now this one is pretty important too. If it's only raining on part of a watershed, then the amount is going to be less compared to if it's raining over the entire watershed. But then there's also an effect of timing. So I think the amount part is obvious. There's less rainfall, so there's going to be less runoff. But it also causes, relatively speaking, a delay in the peak. Because think about how far each raindrop had to travel to get to the outlet. In Storm B, some of the raindrops fall in the watershed very close to the outlet, so they didn't have to travel very far. Whereas in this Storm A, the storm happens to be in the furthest reach of the watershed. So before those particles get to the outlet, it's got to flow over the land and then through the network before it finally arrives. And so that's the cause of why the peak is further to the right for Storm A, is the location of where the drops fell and the transit that it has to take to get to the outlet. All right, now this effect is maybe trickiest of all. And this is something that you often can't see in the rainfall data. And this, when we talk about variability, sometimes just the hydrograph that you're looking at, the historical flow data from a watershed, looks different than you were expecting. So what this is saying is consider two different cases. In one case, the storm was falling on the watershed, and these are both the same amount. Both storm, the first case where the storm movement was from A to B, and when the storm movement was from B to A, the amounts were the same. But what changed is when the rain is going from A to B, those first raindrops are pretty close to A, and so they don't have very far to travel before they get to the outlet. And what they're effectively doing is they're making the channel wet even before the particles get to B. And so in the case of the opposite direction, consider when the storm was going from B towards A. Not only do those first particles arrive at the furthest part of the watershed, but the stream is dry. When those particles are making their way into the stream, it's kind of like that front of water is going through a dry channel. Whereas in contrast, when the storm was going from A to B, as the clouds were moving over the watershed, the rain was wetting the stream, so that when the water finally did get to location B and those drops started making their way towards the outlet, all of the abstractions had already been accomplished. And so it's kind of like the travel time was less when the direction was from A to B, even for the particle that first landed at B. So in the case of the movement from B to A, that raindrop that falls at B, maybe it took 30 minutes. But you put that same raindrop at B when everything else downstream is already wet, and maybe it only take 20 minutes to travel instead of 30. Austin?
So the difference in these two peaks here, could you call that like the abstraction time?
Well, it's partly related to the abstraction time, but it's also partly related to how quickly the storm was moving.
Okay.
So there's two effects that are playing there. Yeah, but one of them definitely is the effect of the abstractions. This is a really important one because we sometimes think about, like, it rained on the watershed, but the clouds are always moving. I mean, it's very unusual for there to be a storm and the storm just stays in a spot. That's what made this recent flooding in South Carolina so catastrophic, was like when the hurricane came, everyone was talking about how it kind of like stalled on the Carolinas, and it was just raining and raining and the clouds weren't going anywhere, partly because there was so much of it. That was the exception. The rule is that the storms are moving around, and so it's not just always the amount of rainfall you got, but what path it took relative to the shape of your watershed. Okay, so let's revisit the definition of rainfall excess. We start off with a hydrograph. This hydrograph isn't inverted in this case. This is just we're looking at, over time, what was the rainfall intensity. Now, rainfall is not the same as rainfall excess. If we subtract out the infiltration, remember the declining potential rate of infiltration, where the infiltration rate is getting lower over time because the suction pressure beneath the soil is decreasing. Those voids, as they become closer to saturated, are going to be drawing the water down with less intensity, and so the infiltration rate is decreasing. So anything that's above the amount that was infiltrated is the rainfall excess. And so we could do like a little mass balance and remember saying a rainfall excess is rainfall minus infiltration. So it's the rainfall excess that is the water that is going to accomplish the abstractions and then contribute to runoff. So what this is saying is there is a kind of like a conceptual workflow. If we want to start with rain gauge data and we want to end up with a hydrograph, what are all of the factors that have to be accounted for before you can draw a hydrograph that shows the expected stream response? And remember, why do we care about the hydrograph? Because the peak of the hydrograph is what we're going to use to size infrastructure. The hydrograph also we have to size storage, like ponds. So it's not just the peak that matters to hydraulic designers, it's also the overall amount over time. Because if we're going to be designing like the size of a pond and how big the outlet from the pond needs to be, then we're going to have to know the entire temporal distribution of runoff from the watershed. Okay, so we start with a rainfall hydrograph, and then we subtract out the infiltration. We also consider the abstractions, other abstractions like the wetting of plants and the wetting of surfaces, and then we have some idea of what's the rainfall excess. Now, of course, we've already talked about why infiltration decreases over time as the voids begin to fill, and we already know that a hydrograph is the runoff, a hydrograph is a representation of the rainfall. Now here's the conceptual analysis steps that we go in. we start with the rainfall. We've talked about how we get to a rainfall excess hydrograph. Now we have to convert this to runoff, and the simplest way of doing it is what's called a unit hydrograph approach. That's what's going to be the main focus of the rest of our time together today, is this unit hydrograph approach. And what a unit hydrograph approach is, essentially, is we're saying for 1 inch of rainfall excess, what will the watershed response look like for 1 inch? And then if we know for a given watershed what happens when there's an inch of rainfall excess, then we can predict what the shape of the hydrograph will look like for other amounts. We'll use that to scale. Now we know that there's other effects, like there's so many other effects besides just the rainfall amount. But the simplest way is just to start with characterizing the response of the watershed to 1 inch of rainfall excess, and then using a scaled approach that we've got an example we'll go through to try and predict what is the hydrograph from that. So we'll use this unit hydrograph approach to tie together the rainfall and the runoff. It's kind of like the proportionality factor. The output is going to be the hydrograph, and then on top of the response to the storm, we move the hydrograph upward to account for base flow, which is the groundwater that's going to be in the channel anyway, whether it's dry or whether it's wet. And so then that gives us the total runoff hydrograph. The total runoff hydrograph will be the storm response water plus the groundwater that's going to be in the channel due to just the slow movement of water through the soil towards the channel. So conceptually, this is what we want to do, is we want to start with rainfall data and end with discharge data. And the simplest way to do that is with the unit hydrograph model. So it's a linear method of scaling the runoff according to starting with an effective unit of rainfall. And so here it's in terms of a millimeter. You could say, for a millimeter of rainfall excess, what does the hydrograph look like? You could do it for a centimeter. You could do it for an inch. Just some fixed quantity of rainfall excess. You figure out what does the shape of the hydrograph look like, and then if you had twice as much rainfall, what you do is you just double the height of the hydrograph. You wouldn't do anything in this unit method. We don't do anything to change the timing of it. We just assume that if there's one, in this case it's saying millimeter, so I'll say millimeter. If you had a millimeter of rainfall, this is how high it gets. If it's 2 millimeters, it goes twice as high, but the timing stays the same. So we're not making any corrections for how quickly it's going to arrive with the unit hydrograph approach, and that's one of the weaknesses of it, is that we know if it's twice as big, it's going to arrive a little sooner, because there's going to be less friction effect. It's not going to be delayed as it moves through the watershed. So this is a simplification that, on the plus side of this unit hydrograph method is it's really easy to apply. But on the minus side is it misses some of the reality of how the water moves through the watershed. So the principle is, once you know how the watershed responds to one storm, you can predict what it looks like for other storms. Now, it's not like you have to wait around until your watershed has exactly 1 inch of rain. It's like, well, sorry guys, we've never had exactly 1 inch of rain in this watershed, so we can't make a unit hydrograph. You make the unit hydrograph with whatever rainfall you get, you scale it down to what would have been the response to an inch. So let's say you have 1.5 inches of rainfall excess in a given storm. Well, you just divide your hydrograph peak by 50%, and then you'd find out what is the 1 inch equivalent of it. So here are some more of those assumptions. Like I said, it's easy to use, but it's assuming that during the rainfall period, there's a constant intensity of rain. So if it's not just a single unbroken rainfall intensity, we have to break it up into time increments. So we'd maybe do an hour at a time and assume a constant intensity within each time step. It assumes that uniform distribution of rainfall across the watershed, that it's raining the same everywhere. It assumes that each time increment is constant, meaning that if we have multiple pulses of rainfall, that each one of them has the same duration. And it assumes that the watershed isn't changing in the short term or in the long term. So what I mean by that is it assumes that if you have 1 inch of rain now and an inch of rain in the next hour, that the first response and the second response are exactly the same except for the time offset. Whereas in reality, the second inch of rain is going to have a different effect than the first inch of rain is, because that first inch of rain is maybe satisfying some of the abstractions. So there's some weaknesses, but it's a good starting point for translating, with the starting point being rainfall data and the finishing point being a hydrograph. It's a good place to start. So the trick becomes when you have more than just a single continuous pulse of rain, because it's pretty improbable that a storm is just going to be like 1 hour long. If you have multiple hours, then you have to combine different unit hydrographs with different precipitation pulses. And so let's say that you are using a unit hydrograph, and you're going to predict the runoff during a rainfall event that's any amount other than a unit of rain. So instead of an inch of rainfall excess, it's 1.5 inches. Then what you do is you're given the precipitation amount, and you're also given the unit hydrograph, and what you want to know is what is the runoff for some other storm. Now, this is a conceptual figure that kind of shows you the calculation approach to find what the hydrograph looks like. But I want to jump just ahead for a moment. We'll come back to this one. This diagram shows the watershed. This figure is showing the calculations you'd use to find the runoff. So let's look at the watershed first. So inside this watershed, if there was 1 inch of rainfall excess, this is the hydrograph that we'd see. So this is the unit hydrograph, this table on the right. Now, this watershed, I've divided it up into bands. Area 1, which is divided by this dashed gray line, this is all of the water that falls in Area 1 will get to the outlet within 1 hour. So these are essentially travel time zones. If raindrops fall in Area 2, then it's going to take some time before it gets to the outlet, because anything that falls in Area 2, it has to travel down through Area 1 before it gets to the outlet. So then Area 3, you can see, is even further away, and so on and so forth. So the rainfall, this 1 inch, it all happens in the watershed from time 0 until time 1. So I guess I should clarify this. Response to 1 inch of rainfall excess during the time 0 to 1. Okay, so the rain happens from 0 to 1, then the response is that at time 1, the flow rate is 10, at time 2, it's 100. Now, why would it be bigger than it was at 1? Because the rain has stopped by now. Like, the rain is only going from 0 to 1. So what we're seeing is at time 1, which is the instant that the rainfall stops, the flow rate is 10 CFS. So why is it higher during at time 2? If the rain stopped, why are we seeing more flow? It's the previous tributaries. It's the upstream area. So if you look, Area 2 was bigger than Area 1. So all of the water in Area 2, it took some time to get down there. So we're seeing there's a delayed response. If we were thinking about doing a graph of the hyetograph and the hydrograph, just briefly, it would look like this. There is, during hour 1, 1 inch of water. So here's time 0, 1, 2, 3, 4, 5, and so on. So it goes 10, 100, 200. I guess this isn't to scale very well. 10, 100, 200, 150, and it's tapering down back to 100. So the rain stopped at hour 1, but it's taking a long time for the rest of the basin to drain. Just think about, you pour water and stuff, it takes a long time for all the water to drain out of it. Even if just the period that the water was being applied to the surface was relatively short, it just takes a long time for the water to move through the watershed. So if we go back to this, what it's saying is, what if it rains for more than 1 hour? This is the response for 1 hour of rainfall. Well, what if there's precipitation not just during a single hour, but what if there's also a certain amount of rainfall that occurred during hour 2? What if it rained during hour 3 as well? So this is kind of like a conceptual equation that's showing you what would be the total runoff hydrograph if there was 3 different hours of rainfall. So what we're going to take a look at in this example that we'll go through together is for this watershed and this unit hydrograph, then what if it was raining for 4 different hours? We're going to go through the process of applying a unit hydrograph to a rainfall where there's 4 different time increments of rain. So this is the calculation approach if there's 3 periods of rain. So what we see is the first block of the hydrograph is the precipitation amount during hour 1 and the unit hydrograph amount during hour 1. Now look at the second block. It's saying the precipitation amount, unit hydrograph 2. That's because what we're talking about now is the water that was in band 2 of that diagram. So the precipitation during the first hour, the unit hydrograph amount for the second hour, and then the precipitation during the second hour and the unit hydrograph for the first. Because there was the rain that during hour 1 was all over here. It's going to take 1 hour to get to here, 2 hours from this zone to get to the outlet, 3 hours from this zone to get to the outlet. Well, during that time that the first pulse of rainfall is moving towards the outlet, what if now there's a second pulse of rainfall over the entire watershed? And so there's like this staggered delay series of precipitation amounts that are making their way down through the outlet. Okay, so let's go through this example because I think, or at least I hope, that this idea is going to make more sense after we've gone through the calculations together. We've got an inch of rainfall excess falling onto a watershed in an hour, and we got this unit hydrograph from the inch of rainfall excess. Now, what is this watershed going to do if we get this rainfall pattern, and we're going to assume abstractions of 0.3 inches per hour? So, in other words, this is not rainfall excess yet. We're going to have to do some calculations to find out what is the rainfall excess, and then apply that precipitation into this unit hydrograph. Okay, so if you've got your computer, let's start up Excel. Okay, so first of all, let's get the unit hydrograph in Excel. So unit hydrograph, and we have the time in hours, and then the runoff. And the units of that is CFS per inch of rainfall excess. Okay, so runoff Q, the units is CFS per inch of rainfall excess. And let me just copy and paste that over. This was our unit hydrograph. You can't copy and paste, you have to type. So this is just given. Someone out there did a study and found out what was the unit hydrograph. And with that given data, we're going to, let's calculate our hydrograph. So we'll have a hydrograph. Okay, so we had a certain time in hours, and during the first hour, second, third, fourth. Okay, and we're going to have precip in terms of inches, and then abstraction in inches, and then we'll subtract the abstractions from the precipitation, and that'll give us the rainfall excess, also in inches. Okay, so the table said that let's look at what happens if there's half an inch, then 1 inch, then 1.5, and then back down to half an inch. Okay, so there was half an inch, 1 inch, 1.5, and then back down to half an inch again. Okay, so the abstractions in the problem statement, it said it's just always 0.3 inches per hour, and that's pretty simplified. We would expect the abstractions to be bigger at the head end of the storm rather than being constant. But just for simplicity, let's assume that that was the case, that there was always going to be maybe in the form of infiltration or interception or something is just going to account for a difference between the rainfall and the amount that is considered excess. Any questions so far? This is just all given data to this point. So we're just doing the first calculation here. So equals precipitation minus abstraction, and that gives us the rainfall excess. So during that first hour, there's half an inch of rain, but 3/10 of it is lost due to abstraction, so 0.2 inches of rain is going to be the leftover amount that will contribute to runoff. Okay, so now what we're going to use this to determine is the resulting runoff hydrograph. All right. And so we have time in hours, and then the we'll call this like period 1, period 2, period 3, period 4. Okay. And we got to go down through 10 hours, and you'll see why it's longer than the unit hydrograph. Okay. So each one of these is going to be the rainfall excess that we're calculating, and it is rainfall excess during the period that's shown. So maybe I'll put like kind of like a secondary description here that what we're calculating is the rainfall excess in inches during the period shown. Okay, so this is what happens when there's an inch of rainfall excess. We only had 2/10 of an inch. So what we should expect is that during period 1, there's not going to be as much rain. So there's zero flow at time 0. We have to key that in manually because it was only implied up here above. But now, during hour 1, what should the runoff be? Let's not do the calculations with Excel. Let's do the calculations with our brain. If it's 10 CFS that you get per inch of rainfall excess, but now we've only got 2/10 of an inch, how many CFS? 2. Very good. Exactly right. What about hour 2? Instead of 100, it's going to be 20. Hey, you guys see where this is headed, don't you? All right, so let's do this. Equals 0.2, and we got to anchor that reference the numbers. So I'm going to put the $ just in front of the numbers. Well, I'll anchor the whole thing because I'm not going to be able to just copy and paste anyway. So 0.2, anchor it, times, scroll up here to the 10 because that's what corresponded to hour 1. So then that gives me the 2 CFS. And then if I drag that down, it's going to tell me how many CFS through each of those times. And then I have to just manually put in zeros for the rest. 0, 0, 0, 0. All right. So any questions about this first step?
Go back to your equation real quick.
So I'm multiplying the given rainfall excess for period 1 by the hydrograph. And only anchoring the reference to the rainfall amount, not anchoring the reference to the hydrograph. All right, so let me make that a bit smaller. Okay, now let me tell you about the most common mistake that people make. Now, this is what happened to the watershed during period 1. Period 1 was it rained during 0 until 1. When is it raining during period 2? That's right. It's raining from 1 to 2. So that's later than the first period was. So what we have to do is we have to shift the unit hydrograph down by 1 row. Because instead of starting at the same time as this started, we want to start the response to the event lower in our resulting hydrograph. And so we typed in the 0 in this first one, right? We typed that 0 in, so we'll put that one in here too. But then we need to put in another one. Because what we're doing is we're saying the rainfall didn't start at the beginning of the time. This now we're talking about this 7/10 of an inch of rainfall excess. And so now what we do is we start equals 7/10, anchor that reference with the $, and then multiply it by the unit hydrograph again. Okay, so starts with 7. The next one is going to be 70. If I drag this down, hopefully it'll say 70. All right. 200 times 0.7, so that'll be 140 and so on. So I drag that down through, and then I have to put in the rest of these as 0 manually. So I delayed it. I moved that hydrograph down a row because period 2 is an hour later. And so the response at the outlet, remember where we're measuring all of these runoff amounts, if I go back to the picture of this watershed, we're measuring the runoff amounts at the outlet. Let me put a little circle at the outlet. Okay, this is where we're measuring everything. All right. So the 0.5 inches of rainfall meant there was 0.2 inches of rainfall excess, which meant during hour 1 there was 20, and then all of that other, that first hour of rain is coming to the outlet in a delayed fashion, one step at a time. But at the same time as that hour 1 rainfall is making its way through the watershed, the hour 2 rainfall is also making its way through the watershed towards the outlet. So now we've got hour 2. Let's do the same thing with hour 3. So we have to type in 0, 0, 0. We have to stagger it. So we've offset it. And then we have 1.2 inches of excess, anchor that reference, times the unit hydrograph amount. And we drag it down through. And it should terminate at 60 because that's 50, the last hour of the unit hydrograph multiplied by 1.2 inches of rainfall excess. And then we put these extra zeros in. And then finally, we'll do period 4. Oh, I almost made a mistake. 0, 0, 0, 0. Okay, we stagger it, and then the first time we see the water is at hour 4. The first time we see the water coming out of the watershed from this last pulse of rainfall excess. Okay, so then the final thing is we're going to have a column that is the total runoff. So this is the total runoff, and this is in terms of CFS. I mislabeled this. I should have called this the runoff in CFS during the period shown. We were using this was the rainfall excess, and each one of these is runoff in terms of CFS. So I apologize for that discrepancy. All right, so this last one is the total runoff. And so what we have to do is we have to sum everything that is to the right, so all 4 periods. And so you're combining together the 4 different pulses of rainfall and their individual stream responses, and you're finally getting the overall delay. And so this was U1, U2, U3, U4, U5, and U6. Okay. If we're going to go back and look at that conceptual diagram, this was P1, P2, P3, and P4. Let me center that. And then this is going to be Q1. Oh, Q1 starts at time 1. So Q1, Q2, Q3, Q4, Q5. There's got to be a better way to do this. There. Nice. Okay. All right. So look at this Q1. What is essentially the equation for it? It was the result of U1 times P1. That's all that was in Q1. But Q2, that was, Q2 was U1 times P2 and U2 times P1. So if I go back to this sketch, I think this will make more sense now that we've been through the spreadsheet, that the overall hydrograph during the first hour is just the first hour's worth of rain, and U1 represents that area of the watershed that will contribute to flow in 1 hour. In the second hour, there is that first amount of rain on area 2 because it takes longer time to travel to the outlet, but there's also there's hour 2's rainfall acting on area 1. Okay, Okay, the third hour is hour 1's rainfall over area 3, hour 2's rainfall over area 2, and hour 3's rainfall over area 1. So actually our hydrograph was more complicated than this because this was just showing 3 hours of rainfall and we had 4. But the procedure can be applied to any number of successive hours. It's just each time, the key that you got to remember is to stagger the arrival of the next pulse of rainfall by an hour. So there was this one, that one, there were 4 of them in total, and during each period we have to offset the unit hydrograph by 1 additional hour. Yes?
Can you go back to that bar
This one?
diagram?
Mm-hmm.
Well, no,
Oh,
picture.
yeah.
I'm having a hard time. Why? In the second set of bars there, why do you have
Mhm.
P1 now times U2?
Because it's the first hour of rain in area 2 because it was in the second hour, it was last hour's rain that's finally arriving at the outlet. Like, let's say
It rains over everything.
it rains on everything
And then we
in
get
the first hour.
one, and 2 hours later we get the effects of.
We get the effects of what was raining here
First hour.
last hour. Yeah.
Okay.
Mm-hmm. And then in hour 3, the first hour's rain in this zone is finally making its way towards the outlet.
That makes sense.
Does that make sense for everybody? Okay. So I think in the homework assignment you have a problem where you have to do this, the same kind of unit hydrograph thing.
But that assumes that the rain for the first hour in the first section is all gone, right?
Mm-hmm.
Period 2.
Yep. Yep. You'll notice if we go back to the equation here. Yeah, so in the second hour, P1U1, that's already gone through the outlet and it's not contributing to the flow that we see now. Like the flow that we see now is this hour's rain over the first area and last hour's rain over the next area up watershed. Yeah. You know, what's really tricky is calculating the unit hydrograph when you're given the P's and the Q's. That's kind of a really interesting process called deconvolution. It's a series of equations where you have maybe like 5 equations, 5 unknowns. It's kind of interesting, but we won't take the time to do a deconvolution as an example today. So again, the unit hydrograph idea is you use some given unit hydrograph to predict how much runoff there's going to be during a storm event that lasts other than the given duration and other than the given amount. So you can extrapolate both time and quantity to find the resulting effect. Yeah, I don't know why I'm showing this again. We've already seen all this. All right. So this is kind of the another way of looking at our answer. You know, the quantities during each hour, and this kind of shows how the pulse makes its way through the watershed. You know, by hour 5, we weren't seeing any more contribution from the area 1. Because all area 1 had completely drained by time 5. But at time 5, there were other areas that were still contributing their flow to the outlet. So it kind of shows like the wave of water and where it's coming from at any given time. Like where was its original origin and what was its original time of contribution.